guys, it's Miss Miklos, and in today's lecture we are going to be exploring the way that an equation of a graph actually affects the graph. And the whole point of this is that we're going to be able to see some patterns so that eventually towards the end of the lecture we will be able to see an equation and be able to go ahead and translate those changes into the graph. So the first thing that I really want to stress to you guys today is that what we're about to do, please do not think of this as, oh, I need to memorize all of these 42 graphs that we're about to go through, because that's not the case at all. The whole point of this set of notes right now is so that we can learn some patterns so that we can later apply those patterns to any particular equation or graph that we may see, vice versa. We can see a graph and then also write the equation. Okay, so I do have a note handout like this up on my Alu Blackboard, so you can go ahead and print that out. And I'm going to start, each column is going to be a different, what we call parent graph, or sometimes we will see it called a basis graph. And each row is going to be a particular type of transformation that we will see. So I went ahead and labeled this first row our parent graph or basis graph. And this very first column that we are going to be working with right here, we are going to deal with the function y equals c. C represents any number, and we call this particular equation the constant. The reason why we call it a constant is because y equals a constant value that is not being changed by a variable. So an example of a graph that is constant would just be a horizontal line. Okay, and I just decided to choose to put it there. There's no particular reason why I put it there. So I'm going to move down now to this next one, and I want to see, okay, what happens if we have an equation like y equals 2? And I know that we all know how to graph something like y equals 2. It means that we would go up 2, and we would draw a straight line through ever y was equal to 2. If it was y equals 5, we would go up 5 and draw a horizontal line. If it was y equals -1, we would go down -1. And that really is all that we can do with a constant graph or a horizontal line here. And we call this a vertical shift, because it is moving the graph either up or down depending on what this number is. And we're going to see whatever the function is, whenever I add a constant value, that's going to affect how the graph goes up or down. We also give this type of transformation a specific name, and we call it a rigid transformation. And what a rigid transformation is, it is a particular type of transformation that does not cause the shape of the graph to change at all. It just causes the graph to move around. And we will see something later on that we call a non-rigid transformation, and that will cause a distortion in the graph. So we've seen so far, if y equals c is our constant, the only change that really happens is a vertical shift. So we're going to go ahead and move on here to our next type of parent graph. And we call this one y equals x, which we call the identity. And that is just a linear equation. Okay, once again, we're starting off with the ones that we're really used to dealing with in graphing, just to make it a little bit more familiar with us. Okay, and some things that I want to point out, things that we know. This is in slope-intercept form, so technically we have a slope of 1 and we have a y-intercept of 0. So notice I started at 0, and it appears to be going up 1 and over 1. So now I'm going to move down, and we're going to see, okay, what would happen if I had an equation like y equals x plus 2? And we learned all the way back in Algebra 1 that this 2 is a y-intercept. So I'm not making my graph totally to scale just to save us some time. Okay, but the important thing is that what this is telling me to do is move the equation up 2 and then draw my line. So once again, we are seeing that this is a vertical shift. So if I'm adding a number here, just like with my constant value, that is telling me how far up or how far down to go. Okay, so with this next equation here, the thing that I want to point out, and you'll kind of see later why I'm doing this, is that I'm putting the function in parentheses. And you guys might be thinking, well, this is exactly the same as the equation up here. And you're right, it is. Okay, but the significance that I want to show us is that technically, if I have a 2 inside the function, okay, so inside the parentheses, we refer to that as being inside the function when the variable's in there. That is actually telling me to go to the left 2 and then go ahead and graph using the appropriate slope. So what we really did here is we took the opposite of whatever number is inside the parentheses. Okay, this is another rigid transformation. And notice this time instead of moving vertically up or down, it's moving horizontally, in this case to the left. So we're going to go ahead and call this one a horizontal shift. And in parentheses there, I said that we are going to think of the opposite. So if it's like +2, that means I'm moving to the left 2. If it's -5, I'm moving to the right 5. Okay, so far we've seen a vertical shift is when we add a number to the function. A horizontal shift happens when we have a number inside the function and we move in the opposite direction. Our next equation here, what if we had something like y equals -x? You guys know that negative means that we really have a negative slope, so it's falling from left to right. So it would look something like this. And what we're going to learn is that whenever we see this negative, that actually means that the function is a reflection in the x-axis. So I wrote reflection in the x-axis, and this is an example of another rigid transformation because it's not changing the shape of the graph at all. It's just changing the orientation of it. It's going in a different direction. And just to review, okay, this is the x-axis. So it's like if I took my original function and folded on the x-axis, it would line up exactly with our new graph. Our next one that we're going to look at is y equals the quantity -x. And once again, you guys might be thinking, well, that looks just like what we just did. And in this case, you are correct. It ends up being the same graph. But what I want to point out is that whenever we have a negative inside the parentheses, it causes a reflection over the y-axis. So this time, if I compared our original graph with our new graph and folded over this line, they would line up with one another. Okay, so a negative out in front is over the x-axis, and negative inside the function is over the y-axis. So I'm writing that that is the reflection in the y-axis. So I zoomed out here just so we could get a general idea here. I know it's kind of tough to see, but here is our identity, here's our constant. And these are the 4 rigid conformations, what am I talking about? Rigid transformations that we're going to be dealing with. So now we're going to kind of transition into the non-rigid transformations. So what if we had something like y equals 3x? Okay, you guys know from previous experience, this 3 is the slope. So this is telling me to go up 3 and over 1. So it is causing a change in the graph. Okay, this graph does not look like the other graphs we've seen. It didn't move up or down. It wasn't a reflection. The slope actually changed, and we are going to give this a specific name. We are going to go ahead and call this a vertical stretch. And if we think about it, it's like I'm taking the graph from the top and the bottom, because that's the vertical, and I'm pulling it tighter and stretching it, and that's affecting what the graph is going to look like. So this is the first of our two non-rigid transformations that we're going to go ahead and see. And the final one that we're going to look at is if it was y equals 1/3 x. We know that this time that means I'm starting at the origin and I'm going up 1 and over 3. Okay, so my line's going to look something like this. And this is what we call a vertical shrink. So instead of reaching at the top and bottom and pulling it and stretching it, we are going to push down and shrink it and make it closer to the horizontal. So I'm labeling this row a vertical shrink. Okay, so we've actually learned our, 6 different transformations we're going to see. Now we're just going to go ahead and look at it with a different parent graph. Our next column, we're dealing with y equals x squared, and we know that this is what we call a parabola. It is a quadratic equation, but we refer to the graph as a parabola. You guys may remember that a parabola, in general, we start at the origin and we go up 1 over 1 in both directions, and it is a U shape. Okay, so that is our sketch of a parabola. And now let's go ahead and use these different transformations on it. So the first one, what if our equation was y equals x squared plus 1? Okay, what we've seen previously in this row is that this causes a vertical shift. So if we're adding a number, that's telling me how far up or down to go. So adding this 1 is telling me I should go up 1 and then go up 1 over 1, up 1 over 1, and draw my U shape. If it said x squared minus 5, I would go down 5 and then go ahead and draw my U shape. Our next graph, if I have y equals the quantity x minus 2 squared, we've seen previously that having this number inside means that we have a horizontal shift. So we are moving the opposite of this number. Since this is -2, I'm going to go to the right 2, and then go ahead and draw my parabola. Technically, we already knew both of these two right here, this one and this one, because that's how in Algebra 2 we learned how to find the vertex of a parabola. So, our next one, if I have y equals -x squared, we know that this negative means it's a reflection over the x-axis. So instead of going up, it's going to be reflected and going down. So negative out in front means it's a reflection over the x-axis. Y equals the quantity -x squared. Okay, this time we have a negative inside the parentheses, which means that it's a reflection over the y-axis. And if we just think for a moment about a U shape is already reflected over the y-axis. So this graph actually ends up looking like our original equation. But that makes sense. If we think about this, whenever I square a negative, it becomes positive. Okay, so even though this looks the same, it really is still a reflection over this axis. It's like everything that was in quadrant 1 moved over to quadrant 2. Everything that was in quadrant 2 moved over to quadrant 1. If we have y equals 3x squared, that means instead of going up 1 and to the right 1, I'm going up 1, 2, 3 and over 1, 1, 2, 3, and to the left 1. And so once again, this causes that vertical stretch where I'm stretching and I'm making my parabola become closer to a vertical line. Likewise, if I had y equals 1/3 x squared, okay, I'm going to go start at the origin, go up 1 and over, I don't really need to draw that dot there. Okay, up 1 and over, 1, 2, 3, 1, 2, 3. And I already said this, but obviously I'm not totally to scale just so we can fit everything. The whole point here is that we're understanding the transformations that are happening. So notice this time this graph, okay, we used to say this was fat back in Algebra 2, but really what it is a vertical shrink. Okay, we're shrinking it, making it closer to the horizontal. So I'm zooming out again, and here we can see that once again, okay, even though we have totally different graphs, the same type of transformation is happening. Now we're going to do this another time with another parent graph that you might be familiar with. Some of you won't be, and that's fine. I think we're going to start to make some guesses as to what's going to happen. And then our last two parent functions are going to be things that you haven't graphed before, and we're just going to know how to graph them based on the patterns that we are seeing. So the next type of graph that we're looking at here is going to be y equals the absolute value of x. And some of you guys may remember that this is a V shape, and it's actually really similar to the way we graph a parabola. And as I already said, this is called our absolute value graph. Okay, the thing that's going to be different, we know an absolute value is a U shape. Absolute value V is a V shape. So let's go ahead and see how this affects our other graphs. If we had y equals the absolute value of x minus 1, that means that we are going to go ahead and have to shift down 1. So I'm going to go ahead and go down 1 and then draw my V shape. We know that this negative, okay, when we're adding or subtracting that value, that is what is called a vertical shift because we're either moving up or down. So looking at this next graph, y equals the absolute value of x plus 2. This time I have a number inside the function, which means it's a horizontal shift, and we're moving in the opposite direction. So I'm going to move to the left 2 and then draw my V. Okay, I'm not being super accurate with my V, but just a reminder, it would be going up 1 and over 1. That's the general graph that we use for absolute value. So I can't stress this enough. What we need to memorize, we need to know if I'm adding a number to a function, that would be a vertical shift. If we're adding a number inside the function, that would be a horizontal shift. Next, to find something like y equals negative absolute value of x, we know that that is a reflection over the x-axis. So instead of my V being here, it is going to be facing down. Y equals the absolute value of negative x. Now, we could think of this in two ways. If I was just thinking, oh, the negative inside, that means that it is a reflection over the y-axis. Well, this V is already symmetric around the y-axis, so I can just go ahead and draw my normal graph. Or you might have thought, okay, the absolute value of a negative is a positive number, so we know that we end up with just y equals the absolute value of x again, which is our original graph. Okay, but key things we need to know with reflections. A negative outside means that we are reflecting over the x-axis. A negative inside our function means we are reflecting over the y-axis. Our next one, y equals 3 times the absolute value of x. I know this is repetitive, but hopefully we're seeing the patterns where this is going to cause a vertical stretch. We're going to go up 3 and over 1 in both directions. So I'm going to go ahead and draw that V shape. Okay, and our last one for absolute value, if I had y equals 1/3 times the absolute value of x, that means I'm starting at the origin and I'm going up 1 and over 3 in both directions and drawing my V. Okay, so once again, we're seeing the patterns. If I have a number where the absolute value is greater than 1, that is when we have that vertical stretch, like we saw up here. Okay, when this number, the absolute value is greater than 1. And the reason why we say absolute value is because it doesn't matter if it's positive or negative. As we know, if this was negative, that would just mean that it is a vertical stretch and also a reflection in the x-axis. Okay, if we have something where the absolute value is less than 1, so we have a fraction that is less than 1, that is when we have that vertical shrink. And last year you guys probably learned fatty fraction, and that holds true. We're just calling it something a little bit different. And keep in mind, obviously, if it's a fraction like 5/4, that would be a vertical stretch because 5/4 is greater than 1. Okay, so now we are going to go ahead and look at a brand new function that we are not familiar with. So we're going to use y equals x cubed, which is what we call the cubic function. Okay, and all we really need to know about this new function is what the parent graph looks like, because all of the transformations are going to be identical to what we've seen in all the other graphs today. So the way we graph a cubic graph, we start at the origin, and then we have a point that goes up 1 and over 1, and a point that goes down 1 and over 1. And when we draw it, we can see that it is increasing from left to right, and there has a little bit of like a squiggle in it. I know that's not a mathematical term at all, but that's the best way I can describe it. Okay, so this definitely is not a straight line. There is a little bit of a curve to it. So now we're going to go ahead and take this graph and apply everything else that we have learned. Okay, so if we see something like y equals x cubed plus 2, there's no need to freak out. We know what an x cubed graph looks like now, and we know that when we're adding a value, that makes a vertical shift. So all we're going to do is go up 2, and then I'm going to go up 1 over 1, down 1 over 1, and go ahead and draw my y equals x cubed graph. If we see something like y equals the quantity x minus 1 cubed, I know this -1, since it's inside the parentheses, is going to cause a horizontal shift. And since it's -1, we're going to move in the opposite direction. So I'm going to move to the right one and then move up 1, down 1. I'm sorry, up 1 to the right one, down 1 to the left one, and draw my y equals x cubed graph. This time we have y equals -x cubed. We know that since there's a negative, that means it's a reflection in the x-axis. So our graph normally goes like this. So if I'm reflecting it over the x-axis, the part that's down here all of a sudden jumps up to quadrant 2. The part that was in quadrant 1 jumps down to quadrant 4. So my graph ends up looking something like this. Okay, so if I went ahead and took this and our original graph and folded on the x-axis, I would see that they would match and they would line up with one another. This time we have y equals the quantity -x cubed. When we see that negative inside, that means that it is a reflection in the y-axis. So this time I'm reflecting over the y-axis. So everything that was down here in quadrant 3 is going to go over to quadrant 4. Everything that was up here in quadrant 1 is going to reflect into quadrant 2. So it's going to look like this. So notice, even though it's a brand new graph, because it is our cubic function, our transformations are identical to what we've done on the 4 previous parent functions. Y equals 3x cubed. You've guessed it, this is a vertical stretch because we have this value here that is greater than 1. And instead of going up 1 and over 1, I'm going to go up 3 and over 1 and down 3 and over 1 in order to draw my graph. And our last cubic function, y equals 1/3 x cubed, this time since this is less than 1, it is a vertical shrink. So I'm starting at the origin and I'm going to go up 1 and over 3, down 1 and over 3. And that was a really bad example of how to graph that, but we get the whole hang of it where it is a vertical shrink because of that value. So once again, here's just a quick overview of everything we've seen so far before we go through our last parent function. Here are all the parent functions we need to know. Vertical shifts occur on all of them when we add or subtract a number outside the function. Horizontal shifts happen when we change the number inside the function. It is always a reflection in the x-axis when we have that negative outside the function. Likewise, it's a reflection in the y-axis when we have a negative inside the function. Those are all of our rigid transformations. Our non-rigid ones, it is a vertical stretch whenever this value has an absolute value greater than 1, and a vertical shrink whenever this value has an absolute value that is less than 1. Okay, so the final parent function we're talking about is y equals the square root of x. And this is clearly the square root function. And what this looks like, we're starting at the origin, and it looks like a sideways parabola, but we're only graphing the top half. Okay, so it's only like the top half of a parabola. So now that we have seen this, sorry, I thought I was on my laser pointer, we're going to go ahead and use the transformations. Y equals the square root of x plus 1. That means I'm going to move up 1 and then move up 1 over 1 and draw the top half of my parabola. Okay, so adding this value, vertical shift. Now we have y equals the square root of the quantity x plus 1, okay? This whole entire quantity is underneath that square root sign. So since I have a value inside the function, that means it's a horizontal shift and we're moving in the opposite direction. So I'm moving to the left one, and then I'm going to move up 1 and over 1 to draw the top half of a parabola, which we know is how we graph a square root function. Y equals the negative square root of x. We know that this means that we are doing a reflection in the x-axis. So instead of all being in quadrant 1, this is going to go ahead and be down in quadrant 4. Now if we look at y equals the square root of negative x, we know that this often would be an imaginary number, but since we don't have an actual value there, we're just going to focus on what happens when we have a negative inside our function. We know that that is a reflection over the y-axis. Since our original function is in quadrant 1, a reflection over the y-axis would bring it into quadrant 2. Y equals 3 times the square root of x. We're going to start at the origin. And since we have this value out in front that is greater than 1, we know that that is a vertical stretch. So I'm going to go up 3 and over 1 and go ahead and draw my square root value function. And hooray, we are finally on our last graph. Y equals 1/3 square root of x. Since 1/3 is less than 1, we know that that is a vertical shrink. So I'm starting at the origin and I'm going up 1 and to the right 3, and I'm going to draw my graph. So this can look kind of overwhelming if I'm just going, oh my gosh, we need to know all these different graphs on their own. And the thing I want to stress once again is we don't. You guys need to know these parent functions. You need to know what those graphs look like. And we need to know what all these transformations, there we go, actually do when we see that in the equation. So now we're going to transition and take a look at some specific graphs and try and figure out what the equation would be. Okay, so now we're looking at the other note handout, and we are going to look at these graphs and determine what the equation should be. So I'm going to be writing down a few things regarding these equations. I'm going to be writing down the types of transformations we see just to help me out. Okay, on your homework, on a possible quiz at some point in time, all I would need to see from you guys is the equation. That's what matters the most. Okay, so I zoomed in here, and the first thing that I notice is that this is a U shape. So I know that the parent function here is going to be y equals x squared. Okay, I know that it should be a parabola. So some other things that I want to notice. I want to look and see, is the vertex of my parabola at the origin? Because that's where the parent graph has its vertex. And I can see here that it's not at the origin, it's actually moved down 1, 2, 3. So I'm going to just make a note that it's a vertical shift down 3. I notice it didn't move to the right or to the left at all, so it's not a horizontal shift. This is still going up, so it's not a reflection. And it also appears that we're going up 1 over 1 for these next points. Okay, so I know that there's not some sort of vertical stretch or vertical shift. So it looks like the only transformation that's happened here is this vertical shift down 3. So we learned earlier that whenever we have a vertical shift, we just add or subtract that value after our function. So this equation is going to be y equals x squared minus 3. Okay, so this is the equation that matches that particular graph. Moving on here to number 2, I can tell right away that this is an absolute value graph because of its V shape. I can also tell that it is not at the origin. Okay, in fact, it looks like it moved to the right 1, 2, 3, 4. So I'm going to make a note that there's a horizontal shift. It did not move up or down at all, and it does not look like there's a reflection over the axis because it's still pointing up. Finally, it looks like it's going up 1 and over 1, so it does not have a vertical stretch or a vertical shrink. So now that I'm writing this equation, I know that when we have a horizontal shift, that goes inside our function, and I have to do the opposite of this. So since it's to the right 4, I'm going to write minus 4. So I just want to point out again, okay, the differences in these two. Whenever I have a vertical shift, we just added or subtracted that value after the function. When it's a horizontal shift, we do the opposite, and it always goes inside our function. Looking at number 3, I can tell right away that this is the identity. It's y equals x. And it doesn't appear that it crosses right here at 0. In fact, it looks like it goes down 1, 2, 3. The other thing that I notice on this line is that it doesn't appear to go up 1 and over 1. It looks like it's going up 2 and over 1, which we know that that's the slope, but if we're being technical, that really means that we have a vertical stretch of 2. So let's go ahead and put all this information and write our equation. So we're going to have y equals, since there's a vertical stretch, that goes in front of our function, so it's going to be 2x. I know a vertical shift goes after, so we have y equals 2x minus 3. And a good way to check, obviously we know how to graph this one, but some of the other ones, if you guys wanted to double check, is you could graph our new equation like in your graphing calculator and verify that it looks the same as what we're actually looking at on the graph. Okay, looking at number 4, first thing I notice, it looks like our cubic graph, so I'm going to write it's y equals x cubed. I also notice that the origin of it is not at 0, it has moved to the left 1. Finally, I notice that this looks like it is a reflection. We know that the normal x cubed graph starts down in quadrant 3 and moves up to quadrant 1, and this is a reflection. And technically on this one, I would accept two different answers because you could argue that this is a reflection over the x-axis, and that's what I'm going to say. Or you could also argue it's a reflection over the y-axis. And I would accept either of those two answers. So I'm going to say reflection over the x-axis in this particular case. And now we're going to take everything that we noticed in this graph and put that all into the equation. Okay, so I'm going to write y equals, since there's a reflection over the x-axis, I need a negative out in front. A horizontal shift always goes inside our function, and we do the opposite. So since it's going to the left one, I'm going to say x plus 1. So our answer here is y equals negative the quantity, or the opposite of the quantity, x plus 1 cubed. Looking at number 5, right away I noticed that it looks like it is a parabola, so it's going to be y equals x squared. I also notice that the point, the vertex is not at 0, 0. It looks like it has moved to the left 1 and down 2. Next thing I'm looking for, it looks like it's a reflection over the x-axis because it's going down instead of going up. And the last thing I'm checking for, does it look like it's just going down 1 over 1? And it does not. It looks like it's going down 2 over 1. So I'm going to say that there is a vertical stretch. Now, even though if it asked just for the equation, you wouldn't need to go ahead and write all these things out. We will have some problems where it is just going to ask you to describe the types of transformations. So that's why it's important that you guys are familiar with the wording, so that you could just go ahead and look at a particular graph and put it into words. Now we're going to go ahead and write this equation. So this one has a lot of things going on. I'm going to start with y equals. Since it's a reflection over the x-axis, I know it has a negative out in front. Since it has a I should step back a second there. A vertical stretch of 2, I need a 2 out in front. Since there is a horizontal shift to the left one, I'm going to put plus 1 because I know it's the opposite. And it is a vertical shift down 2, so I'm going to have minus 2. So this is an example of as difficult as these will get, just because there's a lot of things going on in this problem. Now we're going to the one that looks like the easiest one. Okay, to me this looks like the y equals a constant value. And if we look, it is going through at 1, 2, 3. So our equation here is going to be y equals 3. So sometimes we're going to have ones that are as simple as this. Sometimes we're going to have others that are a little bit more difficult. So we just need to be prepared for whatever we get. Okay, so this next one here, once again, it is an x cubed. It looks like it has moved to the left too. It didn't move up or down at all. The other thing that I noticed here is it does look like there's a vertical stretch, and it's kind of tough to tell exactly where it's at, and I promise you guys on a quiz or a test I wouldn't give you one where it's really tough to see where it's crossing, because it's definitely not going up 1 over 1. In fact, up 2 over 1 it's getting close, but I actually think the best spot where it really goes through that lattice point is at up 3 over 1. So I'm going to say that that is a vertical stretch of 3. So now that I'm writing this, I'm going to write y equals 3. And then a horizontal shift we know goes inside, so I'm going to say times the quantity x plus 2 cubed. And our final one of the day. I know you're like, is this lecture over yet? But I really want to make sure we're feeling good on this stuff. So this time I notice it is a square root function, and that's the first time we've seen it on these 8 problems. I notice that we're not at the origin. It looks like we moved to the right one. It didn't move up or down at all. It doesn't look like it's a reflection, but I can see it's not going up 1 over 1, it's going up 2 over 1. Okay, this one is much clearer to see than our previous problem. This is more similar to what I would expect you guys to interpret. So I'm going to go ahead and write that it's a vertical stretch of 2. So now we're going to take this info and write the equation. So I have y equals 2 times the square root of x minus 1. Okay, and just to review where all this stuff came from, the 2 was our vertical stretch. The horizontal shift to the right one, since it was the right, I did the opposite, and this minus 1 had to go inside the function because it was moving horizontally. So hopefully this gives you guys a good idea of the type of problems you will need to see. If we have a quiz on something like this, I would expect it to be similar to these type of 8 problems where you are given a graph and you're trying to figure out what the actual equation would be.